who is going to talk about another problem in the general area of interest of Renzo Rica and his collaborators. Please.
Thank you, Conrad. Thank you, everyone, for coming. First of all, I'd like to present my special thanks to the organizers of this program for giving me this rare chance to visit Cambridge and give this talk. Today, I'd like to talk about not polynomial invariants in terms of helicity for tackling topology of fluid knots. This is a joint work with Professor Renzo Rica of Milano Bicocca, Italy. Okay, contents. First of all, I'd like to show our motivations for this work. The two motivations here. Two motivations. We will focus on exponential form of helicity. That means to put the helicity on the shoulder. Then we will present our main theorem of this work. Then the proof of the theorem. Before the proof, I'd like to deviate a little bit to revisit knot theory, namely the knot polynomials and the realization of skin relations. After that, for the interest of the researchers in the area of fluid mechanics, I'd like to present some examples about how to compute the polynomials, including the polynomials include triphonals, fake of 8 knot, whitehead, links, and Borromean rings. Okay, motivations. We have two motivations. First is the need of powerful tools to determine topology of fluid knots. The second one is heuristics of quantum transcendent theory. These two guys just lead us to the investigation of these polynomials. All right, topology is important. In fluid mechanics, topology, in fluid mechanics, tangled fluid knots are very popular, including magnetic fluid flux, vortex filaments, and so on. For example, in solar physics, in superfluids, in ordinary fluid flows, and so on. So we need to determine how tangled is a fluid knot. That means to determine the topology of fluid knots. This is essential. It's very crucial because topology is related to energy and other dynamical properties of the system. So how to characterize fluid knot topology? Our current approach for this job is linking numbers. We know helicity. In fluid mechanics, we have a very important topological invariant, that is helicity. Helicity is defined in this way, in terms of velocity and vorticity. Moffat and Rica proved many years ago that for link K of some vortex knots with circulation kappa I, the helicity can be expressed by the self-linking numbers and the linking numbers. Okay, it's a very beautiful result. However, sometimes linking numbers.
Could I ask something? So the link is a discrete subset, and helicity is defined as an integral over the volume. What is the helicity of a link? The helicity is defined as an integral right there.
Yes.
And how you've defined it as on a small subset of the domain. So how is the helicity defined independent of the formula?
In my opinion, it's just defined on the support, which contains all the knots, the whole link.
But the helicity is defined for the entire volume by that integral, correct?
Yes.
So your second line defines the helicity of a link. A link is a small subset of the total volume. How is the helicity of a link defined independent of that formula? Does
You
anyone
mean,
understand what I'm saying? It's the most elementary question possible.
Helicity is defined in the whole volume.
Yes?
You mean why it is related to self-linking numbers and linking
No.
numbers?
What is h of k? Sorry, it'd be so dense.
Ah.
I don't know the definition.
How do you get equation 2? Well,
Or how, I mean, what is the definition of h of script k?
That means in the system we have a family of nodes. So you can just write h, simply h without k. Yeah. So this h just equal to the sum of linking numbers.
Is that the
self-linking numbers.
definition of h, or is that a theorem?
It's a theorem.
And what's the definition of h of script k?
Are you taking omega to be a thin tube around the
Is
vorticity?
it a frame
line?
knot? I mean, I don't understand. What is h of k? Is it framed? Or does anyone know the answer? Where's
I think he's taking it to be a tube around the link.
So it's a frame blank.
Right, in that theorem, you take a tube of some cross-section that's normal to the curve, and then you define a particular vector field in that tube to be perpendicular to the normal slices.
So you choose a framing.
So you're choosing a framing, and you're constructing a tube around the curve from the framing, and then you're taking a particular vector field in the tube, and then the helicity of that particular vector field
is
is
defined.
defined
Properly.
in
So
terms
you've
of the
made
core
some
curve.
choices.
Yeah.
And these choices agree with the ambient field, or they're independent of the choices?
This is only a
The
calculation
meaning
of the
is
helicity
scope
of one
invariant
specific
is
type of
determined
field.
from, first of all,
Specific
the
field, so you
integral form.
just
The second is
arbitrarily
relates
chosen
with,
a frame, a
leading
nice framing
coefficients of
That's
around
right.
the knot, and then
in
compute
general
its
position.
helicity.
It doesn't
Right.
need the
It's
frame.
because
And then it's
continuum
it's
or
equal
other
to that.
Yes.
Yeah.
Self-linking. Right.
Well, that's just the white formula, right?
Yes, that's
So
just
it's
the white
right,
formula.
it's just the white.
Yeah,
Okay,
it's not.
thank you.
it's
You
not-
can even continue.
Each tube has
It's
unit.
Yeah, so,
not deep.
huh?
Each tube has unit flux, and this is how.
Well, right, so it's really of a frame tube around the knot. It's not the helicity of the knot,
Okay.
of the link. Yeah, sorry.
Okay. So then I just continue.
No problem.
All right. However, sometimes linking numbers are not so powerful to detect topology of the system. For example, linking numbers cannot distinguish these two guys, white hat links and Bernoulli rings, and the self-linking number cannot tell this trivial circle and this fig 8 knot from each other. So we need other powerful tools to do the job. So how to find the tools? We need a starting point, which should be a topological invariant. The best candidate is helicity. Why helicity? Because it is a most important topological invariant in fluid mechanics. Let's recall the Edinburgh workshop 2 weeks ago, as well as the IOTM conference in July. In the talks, we knew that helicity is playing a central role in fluid mechanics, both in theoretical aspect and experiment aspect. And we have so many researchers putting efforts in revealing more deeper geometric essence of helicity, including Mihai and Mischberger, their work on higher order linking numbers, and including the work of Jason and Clay on co-homological classes. That's generalized helicity based on generalized Gauss mapping. So we know that helicity is a good candidate, and moreover, we have such a recognition, that is, helicity has remarkable geometric significance. That is, it is a billion Chen-Simons 3 form. It is or Chen-Simons action. So Chen-Simons theory. The generic Chen-Simons action with a non-abelian gauge group is this. Abelian is a degenerate case of non-abelian. In that action, there is a cubic term which labels the non-abelian property of the system. Fluid mechanics is a abelian case because in fluid mechanics, for most problems, we just care about the base manifold. We don't compute the intrinsic space. So the gauge group is the abelian U1. Then helicity. Helicity, this is its definition. In the language of differential forms and wedge products, helicity can be expressed as a three-form integral. Velocity is a one-form, vorticity a two-form. So helicity is an abelian Chen-Simons action. Therefore, it's necessary to have a look at Chen-Simons theory. Chen-Simons theory is very important in mathematics due to the extraordinary success of quantum Chen-Simons theory. The past 2 decades witnessed that Chen-Simons theory is the most important three-dimensional topological quantum field theory, TQFT. It provides a field theoretical justification for knot and three-manifold topological invariants beyond quantum groups. In 1989, Witten, in his seminarial work, Witten used Seagal's algebraic geometric description for conformal blocks to connect Chen-Simons theory with knot polynomials. That's a very beautiful work, and he was awarded the Fields Medal. His work leads to 2 major research approaches in 3D TQFT, just these two guys. In 3D TQFT, we have 3 major approaches. The third one is the perturbative expansions of Chen-Simons integrals. In this area, we have so many famous names, Banatan, Borman-Lin, Guadagnini, and so on, these guys. It has been proved that the exponential expansion of Chen-Simons integrals correspond to, term by term, correspond to Vasiliev invariants via the Kontsevich integral. Borman and Lin proved in 1993 that the Jones, Humphrey, and Kaufman polynomials are special cases of Vasiliev invariants. They just use the exponential form to prove this. So, fluid mechanics is a classical field theory. If the fluid mechanics based on helicity is a classical Chen-Simons theory, so I can compare the classical Chen-Simons theory and the quantum Chen-Simons theory. Compare the 2 classes. Okay. Knot theory has provided so many tools from simple to profound. That is linking numbers, from linking numbers to polynomials, to Vasiliev invariants, to Kovalov homology, and so on. Quantum area, we have arrived here. But in classical area, we stopped here. So our work, the purpose of our work is to push the line to here. So that's our motivation. The targets are the same. Okay, so we want to push the line from here to here by integrating some knowledge of fluid mechanics. So sometimes I just think about this problem. Why previously we have no such tools in fluid mechanics. I mean here. I guess the reason is, firstly, in fluid mechanics, the problem is more complicated because there we have more complicated flux tubes structures. One shell flux tube structure, another shell, another shell. It is not an ideal line of knot. Another reason is, in fluid mechanics, we have, in such a system, we have thousands of crossing sites. That's much more complicated than the ideal case in quantum area. Okay, now let's do some mathematical job. In quantum Chern-Simons theory, a topological invariant can be constructed in terms of Wilson loops. I mean the vacuum expectation value of Wilson loops. Expectation value means a kind of average value. So that is the definition. Here, this is a Wilson loop. This is a action. Action is just a Chern-Simons action. In our case, the action is just a helicity. All right, we notice such a fact that in the case of superfluid, helicity can be expressed as line integrals. This is a very ideal case. This is a very simple case in comparison with other ordinary fluid flows, because it's a superfluid. Another simple case is very thin vortex filaments and thin magnetic flux tubes. Barangay, Rika, and Samuel proved that in that area, helicity can also be expressed as line integrals. Then let's do some work with this line integral and this action. Yeah, if we put the line integrals into the action, then this part will become this. From this expression, you can recognize that this exponential form of line integral is at the center of the problem. So that's an inspiration. This provides us a totally new starting point for studying this problem. That means if we want to find a powerful tool to do the job, we can just start from this exponential form of line integral. Notice, our case is a classical mechanics area. We do not need to do functional integrals. We just start from this exponential form. Here, once again, I want to recall the Edinburgh workshop. There, Dundee group mentioned the significance of a particular kind of line integrals there. And I also want to recall attention to Tom's talk on generalized Aharonov-Bohm effect, where phase is very important. Okay, now let's move to the main theorem of our work. We will give the proof of the theorem. Before the proof, I want to revisit knot theory a little bit. The main results. Okay, for simplicity, we refer to superfluid vortex lines. Here, in this case, the circulations are usually equal. And in this, for thin filaments in quantum fluids, helicity can be reduced to line integrals, where the velocity is induced from the Biot-Savart integral. Then, after some appropriate rescaling, we change the base e to the I something to t to the something. Here t is a formal parameter. By this scaling, and we just for simplicity taking kappa to be 1, circulation to be 1, then we have this theorem. This theorem states that in the system we have a family of knots. The helicity is this. Then this form, exponential form, satisfies the scale relations of the John's polynomial. Here, V is a symbol for John's polynomial. Okay, we should give the proof, but before that, because I mentioned scale relations and polynomials, I'd like to.
Can I ask another question? So when you do the B sub r integral, there's a gauge, right? If you're going to pull back the vorticity to a velocity field, you have to choose a gauge. So how did you choose the gauge?
It is a question. It is a problem. So
velocity is uniquely well.
Well, is he starting with the velocity field, or is he starting with the helicity? Or was he starting with the...
Starting with vorticity, and I think the gauge is determined by the boundary conditions at infinity.
The boundary, so he has boundary conditions.
Yeah, I mean,
That's fine.
open, no walls.
Yeah, no, that's fine.
yeah. And we just consider for the moment some simple case, superfluid case. Okay. Revisit to knot polynomials. In knot theory, Reidemeister proved that any two topologically equivalent knots can be transformed into each other through a sequence of the following 3 types of moves. This one, this one, and this one. You can see there are so many crossing sides there. If a topological quantity is invariant under all these 3 types of modes, this quantity is regular isotopic. If it is invariant under only these guys and this guy, then it's called if it satisfies all the 3 types of modes, it's called ambient isotopic. If only the last 2 modes, is called regular isotopic. Okay, in these modes, we have so many crossing sides. So in knot theory, mathematicians study the problem by studying the different crossing status at a site. That means to study overcrossing, undercrossing, and non-crossing. These 3 guys represent 3 links, which are almost the same but differ only at that particular crossing site. Then I list out some typical knot polynomials. John's polynomial, Kaufman bracket polynomial, Humphrey, and so on. You can see in knot theory, if you define a knot polynomial, you just by giving out its scale relations. Scale relations are a kind of recurrence relations for computing the knot polynomial. For how to do the computations using the recurrence, I will show that in a section of examples. Okay. Then in our coming proof, we will realize the scale relations of knot polynomials. So why to realize that? In a physical system, to find a knot polynomial means to realize its scale relations. If you can realize the scale relations in a system, that means you have found the not polynomial. A typical example is the work of Guadagnini and his collaborators in 1990. In that problem, they just propose a method to construct not polynomials by examining the difference between the overcrossing and the undercrossing. Okay. From you can see that in John's polynomial, Humphrey polynomial, we just care about the difference between the overcrossing and the undercrossing. So, in their work, they directly consider the difference between these two. They consider the difference between the Wilson loops. Wilson loops. So how to pick up the information from this result? They just consider a path, strength as a path, integration path. Then put these two pictures together. Then the difference is just a loop there. A loop will lead to an area. Then in the Chen-Simons integral, this area will lead to operator partial A by using a property of Chen-Simons theory. By this doing, they just derive the desired scaling relations. I mentioned this example because I want to show you that we have to find a mechanism to compare these two guys, to figure out some things from some geometrical operation. All right, if you can do that, if you have a problem, such problem in your system, you can also find such a mechanism to do the job. If you realize the scaling relations, then you solve this problem. For our proof, we need some preliminary knowledge. That is the so-called technique of local path addition. Our strategy is to take benefit of the exponential form and the line integral. Line integral means if you just modify the path, then you can have some addition. Exponential form means addition on the shoulder. In the exponential means the product of factors. Let's take overcrossing and undercrossing for instance. For overcrossing, we just do this. We just break these guys and add some imaginary strands there. These two strands have opposite directions, so they can cancel each other. The same for this. They cancel each other. This is permitted in fluid mechanics. Then we can just cut off this part. Then we have this and this part. That is what we did here. Similarly, for the undercrossing, we can do the same job. What does this mean? Keep in mind that we are dealing with the line integrals. So this path modification leads to split of the reformation of the links there, and this is an exponential form, so we can have product of factors. Okay, then since this n naught, right n naught, has a fixed helicity, this part also fixed helicity, so we can define this guy to be k, and this guy to be k inverse. Why is inverse? Since this guy and this guy, they just have opposite sign in the helicity. By this doing, we re-express this thing as this and this. Then we have two constants k there.
Okay, so hold on a minute. It seems like from that your definition of helicity is basically the total signed crossing number of your diagram.
Yeah.
And what you've said is that if you take a positive crossing and you eliminate it, then that total signed crossing number goes down by 1. And if you take a negative crossing and you eliminate it by splicing, then the total signed crossing number goes up by 1.
Yeah, yes.
Okay, but that's not helicity. I mean, that's a sort of total linking number of the different components plus a sort of diagrammatic writhe of the single components. And that total sum of signed crossing numbers over the diagram is not a topological invariant, right? If I do a Reidemeister 1 somewhere, then I've changed that sum by +1. I mean, if you include the self-integral terms in helicity, you get writhing numbers, which aren't integers to begin with. So, nor are they topologically invariant. So I'm very confused as to what it would mean for a writhing number to obey a Skane relation. But I'm not even sure that Skane relations are geometrically defined.
I think, firstly, I want to emphasize this is a local, very, very local operation. Just as a crossing site, we just, in this neighborhood, we only have one non-trivial thing, just this crossing. And we just keep all other topological things out of the neighborhood.
Right, but that doesn't make any difference to this picture. I mean, surely the total signed crossing number is a sum of signed crossing numbers, which are themselves local. But it doesn't make it a topological invariant.
Comment on this. So usually the Kaufman bracket, when it's defined for a planar diagram with a Skane relation, you have to throw back in t to the minus ride or something like that. I remember what the factors
So you're going to fix it up later by throwing in a
so.
rive term.
Yeah. Yes.
Okay.
I hope so.
Yes.
Okay.
And
Okay. Okay.
all right. Okay. Then, this method can also be applied for this rise, and that rise, this rise. Yeah. Similarly, then we have this two formulas, expressions. Then, if we define, we just give this thing a symbol R of K, then we have these relations. It can be recognized that this side are just the so-called Skane relations for R polynomials, but it's a degenerate case because the parameter Z and K here are not independent. Z is depending on K. Okay, this is only a preliminary result because this degenerate R polynomial is still weak in distinguishing links. For example, for this pair, this guy cannot distinguish these two guys, and those two guys. Okay, we need more powerful tools. Next, we will extend this technique to the case of unoriented links to derive Kaufman bracket polynomial, as well as Jones polynomial. Okay, for our proof, this is a two-step proof. Firstly, we derive the bracket polynomial for unoriented links. Then, based on this bracket one, we just construct the Jones polynomial for oriented knots. Part one is bracket polynomial for unoriented knots. This case is one unoriented knot. This is different from the oriented case in the previous slides. So if you want to use the local path addition, this technique, we have two splitting ways, left and right, or up and down. These two splitting schemes have the same property to occur. So the right-hand side should contain two parts, left, right, and up, down. Okay. The other thing is, during the adding of local paths, we keep the strands with opposite directions such that they can cancel each other. Yeah. Then, in this picture, the blue and the red, the blue ones can form the non-crossing. Blue ones non-crossing. Red ones just contribute to form the unknot. Yeah. Therefore, the right-hand side contains two parts: left and right splitting and up-down splitting. Yes. Here, A, the constant A, is this, where lambda is a constant to take into some uncertainties. It's just details. Lambda running from 0 to 1. Similarly, for this crossing, we have a similar result. So you can find that these two guys are already in the appearance of scaling relations. But for Kaufman bracket polynomial, we need another scaling relations, that is concerning about this disjoint union about the link and a circle. To do this job, we still have two separations. We can start from this one and subtract a path unknot from this rise, and subtract this guy from this one. By doing this, this guy can be expressed in these two forms. Now we have three formulas: 1, 2, 3. From these three guys, we can do some algebra and just solve out this relation. Then we have this, and this. Now, let's endow a symbol for this t to the hk with a bracket. Then we have these relations. These are recognized to be the scale relations of Kaufman bracket polynomial. Yeah. Then the second part of our proof is
All right, I think the fix is
to go from bracket polynomial to Jones polynomial. This is simple because we have standard program in textbooks. We just replace the unoriented link with oriented links, and we just we just give a rising number to the right-hand side to compensate the impact of rise. By this doing, we achieve the scale relations of the Jones polynomial for orientating the knots. From knot theory, we know that bracket polynomial is regular isotopy invariant. That means it is invariant under the second and the third type of red-masked modes. Jones polynomial is ambient isotopy. Yeah, invariant under all the three types of modes. Okay, some remarks and discussion. I want to emphasize that in our operations, we are just doing something for the strength of the link. That means if the strands form a configuration space, then we are doing something in the configuration space, yeah, in some sense. The second thing is, when deriving the Kaufman bracket polynomial, we consider different possibilities. Yeah, this consideration has been inherited in the derivation of Jones polynomial. Yes. The third thing is the above approach are a kind of mathematical observations or mathematical things. Does it have some applications or realizations, real realizations in physics, some physical systems? The last question is how to handle a real fluid mechanical system which has complex flux tube structures and huge numbers of crossing sites in the system. Okay, last section, I'd like to present some examples for the interest of the fluid mechanical researchers. Yeah, examples about how to do the computation of polynomials. As I mentioned, scale relations are just recurrence relations for computing the polynomial. So let me show how to use that recursively. First, the example is right-handed trifle knots, TR. For this TR, we consider this crossing sites. That is undercrossing, overcrossing. Anyway, okay. This one, we wish to use these scale relations because it is a recursive relation. We wish to use that. Then this guy is just this one. This guy is this one. This guy, this one. So this guy can be expressed by this one and this one. That means the trifle knots can be delivered by this triple knot, and this hopeful link. So to get the result of this one, we need to know this and this. This one is already no result. It is a definition. It is 1. For this hopeful link, we need other preparation, some results. Okay, our purpose is to get this hopeful link. But how to compute this hopeful link? We should again use the scale relation to separate this point to be this and this. This one is a disjoint union of trivial circles. This one is a circle, right? For disjoint union of circles, once again we should use a scale relation. The result is this. Then we go back from here to here, and then from this hopeful link to the trifle knots. The result is this. Similarly, for the left-handed trifle knots, we can do the same job and get this result. You can see John's polynomial can distinguish left-handed and right-handed trifle knots because the polynomials are different. Another example is figure 8 knot. We still have this reduction. The result is this. White head link has this splitting. Result is this. White head goes to figure 8 and Hopf link. And the Borromean rings, we can do this crossing point, and this rings goes to Hopf link and the white head link, link. The result is this. All right. Now let's have a look at some practical applications. For practical applications, we can just go back to our original position to replace tau to be e to the h. T goes back to e. Okay, now not polynomial for vertex tangent of tangle of filaments become a function of topology, and this one, this helicity of a particular shape, just raised unknot. This one can be interpreted as a reference mean field helicity of the physical system. And then this guy can be thought to be a gauge for mean rise helicity of the background flow. Then the polynomial goes to be such a function of the topology and the circulation. Averagely, we can take the lambda to be half, and this one just a half kappa square. We can just replace tau with this one because we have this. Then we have some typical results for some typical knots. Yeah, so this paper has been published in Journal of Physics A. Then for future work, we want to keep pushing the line to here and here. We want to extend to Wasiliev phenotype invariants, and we want to do some physical realization of this program. We hope we can do that. And we also want to do some numerical work for this job. We can do these things, this. Okay, so that's references. Thank you very much.
Questions?
Yes, so one of the reasons why these bounds in terms of helicity were cooked up was to get lower bounds on L2 energy. So is there any statement that you can make about how that depends on one of these polynomial invariants? I'm just wondering what's the actual...
I think that's our future work, I think. Just L2 energy. Maybe we can just use O'Hara, Jane O'Hara's definition of energy for knots. Yes, that's our future work.
So I'm awfully confused. Maybe you can help me out. As far as I saw, this is completely a statement about framed links, right? And you're saying that under isotopy of a framed link, the framing plus linking number is conserved, and it's conserved under the skein relation. which is sort of a standard thing, and it's fine. And it would obviously be interesting to extend that to something over an entire vector field, but I have no idea how you propose to go about doing that, or if you claim to have done it, or if you just claim to have sort of repeated Kaufman's observation about framed links. So is this for a field in space, or is this for a field concentrated on a few lines, which is to say a framed link in space?
I think it's you just pick up a subset of, in terms fluid dynamical terms, you just choose a discrete set of vortex tubes in a continuous field.
Sort of infinitesimal vortex tubes.
Yes. This is one possible approach. I'm not quite sure, but in the magnetic context, any lower bound on energy will be a good thing to have. So even if you cannot manipulate the whole continuous field, but you derive a lower bound on energy based on topology, even by picking arbitrarily a set of characteristic magnetic lines, for example, and noticing that these are non-trivial topology, therefore the whole thing must have a lower bound on energy because certain subset has particular topological properties. This will be a valid statement.
If your field happens to lie in a finite collection of closed flux tubes, which is tangent to the boundary to, and that collection forms a link, and the field inside each tube is parallel or is normal to the cross sections.
Yes, yes. So it's either the whole field miraculously happens to be of that form,
okay,
or you pick out a subset of field lines. Sometimes you can, sometimes you can't. If it's, for example, it's fully chaotic, there's no meaningful set of tubes, but sometimes there is.
I see. If the field happens to have
a meaningful subset of tubes, even if they're embedded in the continuum.
That's okay. If it happens to have within it a field that's
doesn't
supported in
have
the
to.
proper way on a set of tubes.
Yeah.
Yeah. Okay.
If it's fully ergodic, then you're stuck.
Right. Okay. So a generic.
You have to be a bit more refined, I think, then.
I mean, it could be that there's
Make them really infinitesimal.
L2 bounds that are independent from local framing, so they extend for any arbitrary field.
Yeah,
There could be.
There could be.
I mean, that's
such.
I would think that's the hope.
That's sort of the hope,
If all
yeah.
you know is these lines, then
Right.
it doesn't matter what the ambient field is, as long as it has to be locally parallel by continuity, and that independent of that, there could be a lower bound of the energy. I mean, that's kind of what you have with a single knot in R3, right? I mean, you have this extension.
You're saying that if a single line is enough, it doesn't have to have a neighboring tube.
No, yeah, well, no, I'm just saying, I mean, as a mathematician, how you would approach it would say, let's say we have this single tubes. They are sitting in a field, so they extend somehow. Different fields extend in different way. If I have an energy bound that's a lower bound independent of the extension,
yes.
then we're in business, and I think that's the hope, and that's
Exactly.
That's
what
why
we're
I asked
talking
about
about.
Exactly.
energy, because obviously
Bishop.
L2
Right. But
continues.
you sort of can't, because
Right.
it's only on a measure zero subset of the space, right? I mean, there's no the energy from helicity is going to go dependent
I think
on
Misha
flux.
has a
Sorry.
comment on that.
Yeah.
I would like to make one simple remark about all these topics, because we hear a lot of talks about individual
Sure.
invariants of
Where's it?
links and
Yes.
nodes. But in physical, there are two, I guess, interesting physical problems in real physics. One is like fluid dynamics, it's magnetic reconnections. And in this, the main problem is not mathematical problem, it's physical problem, what kind of reconnection we have. If we define exact definition, in my old paper we have some construction. So in these cases, the result is more or less simple, that only asymptotic Hopf invariant exists and all others disappear. The second problem is about situation in superfluid helium like 4 and 3. There are a little bit different situations because in this case, vortices are stable. And such things like linkability of vortices, maybe it explains some effect of weak turbulence in these fields. But all these invariants really not help if we can define all such invariants for tubes or real, because there are some ergodicity, as you said, and individual linking coefficient changed. But for tubes, there are some what we call average. And for this, there exists. And this will be interesting to define not this invariant like Jones or Kaplan and so, which are absolutely useless in such problem. But if we can determine something for tubes or more thick object which located our vortices or so, in this case it will be interesting.
Yes, my comment on superfluids is that in superfluids there is a very interesting problem that you have individual vortices, but when temperature is not too low, they are organized in bundles. And bundles imitate normal, regular fluid vortices, but inside they are perfectly discretized. So they're bundles of angstrom-wide vortices have macroscopic behavior of macroscopic vortices. And this is why people believe that this is why you observed perfectly classical behavior of superfluid turbines, although because there are these bundles that imitate macroscopic vortices. So in that context, that could be quite useful, actually.
Okay, so that's a class of physical flows in which...
So this is where you always have the conditions that I said before.
Right.
You always have subsets of tubes, very well defined.
I see, closed finite tubes.
Yeah, but bundles are of interest, or many of them. Any other comments? Thank you very much.